Okay. Just to make sure everybody can see my screen, right? Yeah, okay. So I'd like to ask everyone to turn on their video. It will be really helpful because lets us see your reactions to what we're talking about, and we'll be able to communicate better. So if you guys can, please turn on your webcams, and that'll be great. Okay. And then yeah, thanks, Aaron. Uh yeah, I'll go on. So we're gonna start with the review of our homework problems. Uh, so this week I don't think we got any submissions for the homework. Oh yeah, Aaron, that's fine. Yeah, so we didn't get any, I don't think we got any submissions for the homework, but like yeah, as Shamik said, even if you have like incomplete solutions to a problem, like you can just like take a picture of it and send it to us via email, and then we'll like give you feedback. Or you can send it in Discord. Yeah. So yeah, here's our first homework problem we're gonna review. Four equal charges are located on the corners of a square. What is the magnitude of the electric field at the center position of the square? Um, so Jacob, do you have any idea on how to do the problem?
Yeah. I think if you were to draw it, I think it should, by symmetry, it should be zero, right?
Yeah, yeah. So yeah, good answer. So let's draw the square, and then okay, this is our square, and then I have charges on each corner, right? And then yeah, so I have a charge here, and I'll just call the charge Q because they all have the same amount of charge. At the center of the square, um, you gotta remember that the force is a vector. So you know, if I imagine putting a test charge at the center of the square, uh, there will be a repulsion from this charge over here, right? So that will be in this direction. And then, there are electric forces in all four directions and they're equal magnitude. So they're just gonna cancel out, and yeah, you're gonna get total force is zero. So yeah, great job. Let's move on to the next problem. Uh, wait, there we go. Find the electric field, both magnitude and direction at the center of the square charge distribution shown below. Note that the charges are not equal. Assume that the sides of the square have length L. Uh, Chapman, do you have any idea on how to do the problem? If you don't, it's okay. Just let us know, and we'll try to guide you through it. I guess he's not here, so Aaron, do you wanna type in the chat? What's your thoughts on this problem? What are your mental processes? Oh, okay. Okay, then Jacob, do you have any idea on how to do the problem?
Let's see. So I guess if we have like a point in the center, we could just apply Coulomb's law four times and split it into components.
Yeah, hold on. Yeah, yeah, that's actually a great idea. So, do you want me to take over from now, or do you want to keep going? Because it'll be really good if you keep going. So, yeah.
Okay, I guess let's see. Uh, is there,
Uh,
so what if I draw like a point here? Like, for example, for that corner, that one will be L over 2. Okay, this is L over 2, and we should probably use the Pythagorean theorem to find like the total R. And then, uh, well, let's see. Um,
it's okay.
oh wait, hold on. Hold
Okay.
on, hold on. So what, the total force as a result from that one, sorry, wait. equals, let's do a big Q for like that little test charge and then negative 2Q. Multiply that by K and then the R squared. Um, R is the square root of L over 2 squared plus L over 2 squared. Um, what is that?
Yeah, so
Um,
you're you should be getting I think
oh right, I could just square that as well because it's supposed to be R squared on the denominator. L squared over 4 plus L squared over 4. L squared over 2.
don't forget you need the shoot, sorry, square root on the L. Uh because you're
Oh, right. Oh,
actually
so
sorry,
it
no,
should,
no, never mind. It's fine. It's fine. Sorry, my bad.
oh,
Yeah,
oh, never mind.
you're good. You're good.
So it should just be L squared over 2 here.
Yep.
Uh, yeah, and so that's like one of the magnitudes. So which way does that point? If that's positive, it should go towards that side.
Yeah.
And for the 2L, it's the same magnitude, but it goes in the opposite direction. So I think the horizontal component should cancel out. So I think if you just do the sine of 45 degrees, you should get the vertical component, and then you can multiply this by 2 because there's two of those forces, right? So that's like the net force as a result of the two ones on the right. And then you could probably apply like the same argument to the ones on the left. It's just that the magnitude's going to be half as much,
Yeah.
right? Let's see. So this one, it goes over there. And oh, no, the
No.
opposite direction. It's like that one will cause it to go that way. That one will cause that force to go this way. In which case, uh, well, I guess I could do the same thing. I think you get the point, right? I hope.
Good job. So yeah, so you'll find that way 2q negative 2q it's that way, and then from the plus 2q it's that way. So the net force will be upwards, right? And then
Hmm.
you'll find negative q is that way, right? And then
Yes.
plus q is that way. So you'll find net force downwards. So and you'll just need to add those two vectors together and then you'll get your final answer. So yeah, it's just a bit of calculation, but it should be fine. Let's move on to the next one. Three charges are on a line. The left charge is like I'll draw this out. We have a line, and then the left charge is okay. So this one is Q1, which is 2 nanocoulombs, and the middle charge is Q2, which is 5 nanocoulombs, and the right charge is Q3, which is negative 3 nanocoulombs. And then these two distances, they're both 2 centimeters. What is the force on the middle charge? So this is again another matter of like just applying Coulomb's law. So Q Q1 that's gonna be positive, right? So Q2 is also positive, so you'll get so it'll be a force between Q1 and Q2, and then between Q2 and Q3, it will be in this direction. So once you figure out like you have the distance is 2 centimeters, and then you're given all the charge values. So it's just a matter of applying Coulomb's law and adding these two values together. Uh, Only tricky point of this problem is just make sure that you're converting centimeters to meters and nanocoulombs to coulombs. Um, because remember the units of like like if you want to express your force in the units of newtons, you're gonna need to use like meters and like coulombs. So yeah. Uh yeah, let's move on to the next problem. Unless anybody has any questions on these problems, just like uh put a message in the chat and we can go over them in greater detail. Okay, how much electric force does an electric field of 50 newtons per coulomb apply on an electron? Yeah. So one number for us basically testing you is just you need to make sure that the electric force due to an electric field. So uh if I have a charge over here, uh I'll draw if I have a charge Q over here, then there's an electric field. Remember, like example, if the electric field at point Q, like this is direction of electric field, I just remember that the force on a charge will be equal to uh the charge of the charge and then times the electric field at that point. So remember, they're all vectors. So here it will just be 50, your answer will be 50 times the charge of an electron, uh newtons. So yeah. Uh yeah. And then number five is cool. Particle with charge 2 coulombs and mass 4 kg starts stationary in a constant electric field of 20 newtons per coulomb. How long does it take for an electron to move 22.5 meters? Yeah, so remember, so let's first draw a diagram. So it has charge Q, which is 2 coulombs, and it also has M, which is 4 kg, right? Okay, and then I have a constant electric field of 20 newtons per coulomb. So for example, I might have the electric field, it's pointing towards the right, okay? Then that means like the force on this charge would be F would be Q times E, right? So it will be 2 coulombs times 20 newtons per coulomb, and that's going to be 40 newtons, right? 40 newtons. And then I want to know how long does it take for a electron to move 22.5 meters? Well, if force is 40 newtons, then this also equals to ma, right? By Newton's like second law. So, and since m is 4 kilograms, you know that a would be uh 10 meters per second squared, right? So now you want to find how long does it take the electron to move 22.5 meters? Well, here you just use your kinematic equation, right? So you know that like the displacement, right? That's delta x equals to the initial velocity times the like delta t and then plus the a delta t squared and then divided by 2, right? And then here we're given it starts stationary, right? So V0 is just 0. Delta x, we're given it's 22.5 meters. So I'll put that in 22.5 meters. And then acceleration we just found is 10 meters per second squared. So divided by 2 would be 5 meters per second squared, right? So you just solve for delta t and you'll get, let's see, 22.5. So so delta t squared uh would be 22.5 divided by 5, which I think is hold on, it's like 4.5, I think. 4.5 uh yeah, 4.5 seconds squared. So you'll get delta t should be equal to uh square root of 4.5 seconds. Uh yeah. And then yeah, so this was a bit of a like EM plus like simple mechanics problem. So yeah, it's a pretty good problem, I'd say. Yeah, does anybody have any questions on this? Because it might have been a bit hard to understand. Are you sure? Okay. Right then, if not, then I will move on to the next problem. Okay. How about Shamik? Do you want to explain this problem?
Yeah. Okay, so what we're gonna do is draw the slab. Since we know the slab is conducting, then we know that like all the charge Q will be concentrated at the like the top and the bottom. Uh, so we can just say Q here, and then we'll draw our cylinder. So this cylinder is the Gaussian surface. So now we'll use Gauss's law. So if this is R, R, um, then can somebody tell me how much charge is within the Gaussian surface? Anybody? Uh, okay, that's fine. So we know the surface charge density is sigma. So sigma times this area will give us our Q inside. That area is simply pi r squared. So that's the charge there. That divided by E naught will equal our integral E dA. And from a infinite slab, the E will always point up above it and like down below it. So down, down, right? Um, so the dA vector here is perpendicular, so the cross product, the dot product is zero. So you can ignore that. Since the Q is concentrated here, then there's no electric field below. So we can ignore this one also. So all we have is E times this area, and that area is pi r squared, right? So you can solve to get E equals sigma over E naught. And then the next problem was about an infinite non-conducting slab. And what will happen with the non-conducting slab is that Q will be throughout, like the Q will be throughout the whole slab. So then there will also be a flux through this thing. This flux will also be E times pi r squared. So then this will become E times 2 pi r squared. There'll be two of these. So then for that case, we'll get sigma over 2 epsilon naught. So this is the conducting and this is the non-conducting. Any questions about that? As for like choosing the Gaussian surface, um, there's pretty much only like a few options. You have like your sphere, cylinder, that's pretty much it. And sphere would be hard to work with here because with a sphere, you'd have your E would always be up, but A will always be perpendicular to this. So the angle between A and E will always be changing, and that'll require more integration, like more trig, more integration. And so we choose a cylinder to make that simpler. Uh, okay, I don't think there's any more questions, so move on. Next slide. We covered this. Next slide. Do you want to do this?
Yeah, sure. So prove that the constant k is equal to 1 over 4 pi epsilon 0. So, or epsilon, yeah. So this is referring to, you got a point charge q over here. And then if I'm at a distance like there's this distance r from the charge, and I'm looking at this point over here, then the force like the electric field there, it will be pointing outwards that way, and it will be equal to like, E as a function of R would be equal to like uh KQ over R squared, right? Remember, this is the electric field, not the force, so there isn't that extra like test charge like term over here. So yeah, this is the electric field, and like K over here, right? So K, we want to prove that this is equal to 1 over 4 pi epsilon 0, right? So, or like it says epsilon, but like in a vacuum, it's called epsilon 0. Okay. So now how are we going to prove this? Well, so let's construct a Gaussian enclosure, right? So our Gaussian enclosure would be, oh, I didn't draw that too well. But what we're going to do is we're going to make a Gaussian enclosure around the charge, and it's going to be a sphere. So because of like the symmetry, right? So it doesn't matter what direction you're like it doesn't matter like, okay, so if I say this is a vector r from the charge to the point under investigation, it doesn't matter what direction the vector r is. Like all I need to know is the magnitude of the radius vector, and the electric field would be the same. So like everywhere across the surface of the sphere, I have the same magnitude of electric field, right? And then you got your formula for like your Gauss law, right? So you have the integral over a surface of the electric field, dot onto the infinitesimal area segment or area patch. That should equal to uh your enclosed charge, right? Q enclosed divided by epsilon 0. And here, everywhere across the surface, your E is constant. It's always equal to it's always equal to KQ over R squared, right? So we have that K KQ over R squared, right? So if this is the E is constant, so I can pull it out of the integral, right? And it's also always perpendicular to the dA, because what dA represents is like if I have a small area patch on the sphere, the direction of dA would be like it will be perpendicular to the surface, and the magnitude would be like the magnitude of this area patch, right? And notice that it's always parallel to the electric field at that point. So this integral is just equal to integral of E times the dA, because like we can remove the dot product, right? And then since E is constant, we can also pull it out of the integral. So this is equal to E times the integral of the area, right? But that's just the same as the surface area, right? So your integral would just become E times 4 pi uh, r squared, right? And this should equal to KQ over r squared. Or sorry, 4, yeah, wait, hold on. Oh, yeah. So E is equal to KQ over r squared. So if we find that, that will be equal to uh KQ times 4 pi. Yeah, 4 pi. And this equals to Q enclosed over epsilon 0, right? And Q enclosed, that's just Q, right? So if you cancel out the Q on both sides, you're going to get K would equal to 1 over 4 pi epsilon 0. And that completes the proof. So yeah. Uh, this might have been a bit hard to understand. So like if you guys have any questions, like you should message it in the chat. I see a few more people have joined. So yeah, right now we're just going over uh, proof of that the constant K in the Coulomb's law, or also in like the formula for electric field at a distance from a point charge is equal to 1 over 4 pi epsilon 0. And basically what we did is we just made a sphere, a Gaussian enclosure that's a sphere with the charge at the sphere center. So yeah. Uh, okay, if there aren't any questions, then we will move on. Yeah. Okay, so we're gonna start our class. This is oh shoot. Alright, so our class today will be about electric potential, and Shamik, why don't you tell us about it?
Yeah, so I'm gonna cover electric potential. So first thing to cover is that electric force is conservative. You may have heard of conservative with respect to gravitational field. So basically conservative means that if we bring it if we like if a charge is going through the electric field from point A to point B, no matter the path it takes through the electric field, it'll end up with the same change in energy. Um, so basically, this just tells us that we can find a simple potential energy equation. So we can find this to be U equals K times Q1, Q2 over R. Um, you can find this with U equals integral F, U equals negative integral F dr. And you'll get this. Yeah, next slide. And then related to, okay, so we had U equals, just as a reminder, we had U equals K Q1 Q2 over R. So then we can define electric potential as the amount of U per unit charge, per unit test charge. So we can say U equals K, Q is the charge that we've placed, Q test is the test charge over R. And from our definition, it's per unit test charge. So you'll get KQ over R. And the units for this will be called volts, after like a famous scientist. And so as I was talking before, we can move a particle with charge Q from point A to point B. So in this, the delta U will equal Q delta V, which is like VB minus VA. And from, and we also know that work done by the work done by the electric field will equal negative in the change of the electric potential energy. So yeah, we get this. And you should so in general for problems, they'll usually define the electric potential to be zero at like an infinite distance away from your like setup. Like if you just had like this positive charge, positive, and you had this electric field emanating from it, then we'll designate zero to be at some very far distance away. Um, and then when you get closer, your electric potential will increase, right? And you'll get this. Um, but you should look at the problem. Some problems will define uh potential to be zero at like maybe the origin if it's on the coordinate plane, or just yeah, just watch out for that. Next slide. So we're gonna do a practice problem. I'll give you like 1 or 2 or 3 minutes. You can message me your answers when you have it.
Oh, yeah, also, just as a note, the diagram, I don't believe it has anything to do with the problem, so you can just ignore it.
Okay, I think we should go over this right now. Does anybody have any ideas? Nobody sent us answers, I think, but if you have any ideas, you can say them out loud. No ideas? Okay, let's at least draw it. So we have particle A, 5 coulombs, particle B, -2 coulombs. So we have particle C is 3 meters away from particle A and 9 meters away from particle B. So we can draw like here-ish. This is 3, this is 9. So electric potential energy of particle C given as charge -3 coulombs. So, Jacob, can you tell me the expression for electric potential at C?
It should be K times 5 coulombs over 3 meters. Yeah, and then the other one, it should be K times -2 coulombs over 3.
Over 3?
Wait, is it? Oh, never mind. 9 meters. Yeah.
Yeah. And the thing about electric potential and electric potential energy is that they're additive. So we're going to add the electric potential from A and the electric potential from B. It's like we're superimposing the electric potentials. So yeah, you're going to get this is your expression for V. I'm not going to calculate it. You can calculate it if you want. Uh, electric potential energy um, will just be Ryan, what's electric potential energy in terms of electric potential? Or anybody can chime in. Okay, it's Q times V, right? So this will just be like the charge of C. So it'll just be -3 coulombs uh times this expression, right? This entire expression. Okay, any questions about that? Okay, next slide. So we'll present another definition of V, which is in terms of electric field. So delta V is negative E dot dr. So in other words, if you're looking at the difference in potential between 2 points, A and B, then VB minus VA will equal the negative integral of A to B of the electric field in that region times dr dot dr. So this tells us that electric field points from higher to lower potential. Because if VB had a higher potential than VA, this expression would be positive. And because of this negative, this expression will be negative, which means that E points from B to A. So then, uh, yeah, we have this, right? If you see the example, uh, this is your electric field lines. These are your, like, for example, if you had, this is B, this is A, then the difference you can calculate with this. And another important concept about this is that no work is done along a path on an equipotential surface. So first of all, an equipotential surface is like, as you might guess, it's a surface where the potential is the same at all points. So in this like 2D case, we have equipotential lines. So at these lines, the voltage like along this circle is always the same. So the voltage at C will be the same as the voltage at B. And because of this, you can say that delta U, we're looking at in between B and C right now. So delta U equals Q delta V. And since delta V is 0, this equals 0. And we also know that W equals delta U, or negative delta U, which is 0. So no work is done by the electric field or by somebody like pushing the charge when it's going along an equipotential surface. You can also see that in this diagram. Uh, yeah, any questions on that? All right, next slide. So this is an example. Um, 12 electrons of charge E are equally spaced and fixed around the circle of radius R. So let's say this is radius R, and it's kind of like a clock, I guess, in a way. So you have 12 electrons. This is a kind of a bad diagram, but they're equally spaced, right? And then relative to v equals 0 at infinity. So again, so this it'll be 0 at some very far distance. Then find the electric potential and electric field at the center C. Okay, I'll give you like a few minutes to think about this. Then I'll go over it. Even if you don't have an answer, you can always send me what you're thinking or like an expression. You don't need to evaluate it if you don't want to. Okay, I think we'll go over this. Um, so okay, so we'll find E first. So uh sorry. Yeah, good job, Tony. The electric field would be 0. Do you want to explain it?
uh, I guess the 12 electrons are all symmetric. So if we look at the equations, R goes off to infinity and the poles cancel out. So relative to that, it should be 0.
Yeah, good job. So basically the if you draw it, the electric force from this electron will point this way, but from this electron will point that way, so it'll cancel out. So electric field to be zero since it's like symmetric. All right, we have electric field is zero. And then how do we find V? So V, remember it's additive, so we'll just add the electric potentials due to each electron. So 12 times K, the charge of each electron is E, divided by the distance to point C, which is the radius R. So you just add them all up. Yeah. Any questions about that? Okay, next slide. So we can find the potential due to a dipole. Again, a dipole is you have a positive charge and you have a negative charge and you have this distance d between them. So to find the potential due to this dipole at like, oh wait, let me clear this. Okay, positive q, negative q, d, and then we have our let's find VP, right? The potential at this point P. So the potential at point P will be Q times the distance to the positive charge plus Q over the distance to the positive charge is R plus, and then we'll add the potential due to the negative charge, which is negative Q over the distance to the negative charge, which is R minus. So you can simplify to get this. And like with some like math, trigonometry, whatever, um R minus minus R plus, R minus minus R plus will give you around D cosine theta, and R plus times R minus will give you R squared. So then if you simplify, you'll get K K Q D cosine theta. Oh, sorry, theta is the angle defined here to the midpoint of the dipole. And then that divided by r squared. And r is defined as the distance from P to the midpoint of the dipole. And then usually physicists will denote QD as the dipole moment P. You can see this P. This is just like to simplify the expression, and it's just useful. So yeah. Any questions about this derivation? Uh, okay, moving on.
Oh
Yep.
yeah, and just as a note, remember that like this result it only works, hold on. This only works when you have your when you're at like a really large distance away from your dipole so that the separation between the two charges is much less than the distance from like your point under investigation to the dipole. Otherwise like the approximations we make they won't hold. So yeah. Yeah, let's move on then.
And note about approximations, you should if you don't know a lot of approximations, you should search them up. But like for like trigonometry, like we'll do sine theta is around theta. Cosine theta is approximately 1 minus theta squared over 2. But generally, when approximating, we will ignore second order terms. I know there's a second order term here, but whatever. We'll ignore second order terms. Second order means that um, like delta x is raised to the power of 2. So we'll ignore second, third, fourth, because those are like very small. Because you have delta x is less than 1, and delta x squared will be like very small. So we just don't really care about that. Um, yeah, that's pretty much it. Okay, next slide. So a general strategy for finding the potential due to a continuous charge distribution will be to like okay, wait. Like let's say I have like a ring and I want to find the potential at wait, let's say I have like a ring. This is like a vertical ring kind of. And you have like a distance like let's say it's R, a distance Z away, and you want to find the potential here. Then like it's like you'll get an expression for dv as k dq over the distance from this point to this, which is from Pythag, it's big R squared plus Z squared. And like an important thing to do is that this is obviously the important first step. And an important second step is to write dq as a function of small segments of this ring. So usually you'll be given some charge density of the object. In this case, like lambda, since it's a linear thing. So you'll write lambda times dx, right? Um, so this is just like a general strategy. X, again, X is like R in this case. Um, Yeah, and important thing is that there's no vector components. So like while electric field is vector components, so stuff will cancel out. Here potential is a scalar. So it's just additive. So it's simpler in a way. Okay, next slide. So we'll do this example. I'll give you some time to work on it and then we'll go over it. It's basically the potential due to this charged rod with uniform density lambda.
Oh, yeah, by the way, so like to do this problem, you're gonna get an integral. I don't think it's integrable easily, so like you can just leave your final answer as an integral. You don't have to solve for it.
Yeah, the important thing is learning how to set up the integral and simplify as much as you can. The math you can always learn on your own or just do it. But yeah. Okay, I think I can go over this. Does anybody like, okay, wait. Uh, Jacob, do you wanna tell me how you set up the integral?
Yeah, sure. So basically, from okay, well, first, I guess okay, I'm just on the screen. Hold on. So if you oops, change the color. I guess voltage is equal to this dk dq over r, and okay, and then I found the linear charge density, I think, right, uniform. Yeah. So I put that as like the total charge of that divided by the total length. And dq is equal to lambda dx. Okay. And r is like the distance from like at any like little dq from the rod, and I just called this distance x. So r is square root of d squared plus x squared. Okay, and then I just plugged it all in. Okay, dq is lambda dx divided by square root of d squared plus x squared, and that should range from 0 to L. So that's like the initial setup that I did.
Yeah, good job. Does everybody get that? So um he basically had dv equals
Dạ
k
con nó nói chị điều kia
dq
chị vừa chị nói chị uống không
uh dv equals k dq over r. So then he got d equals k integral dq over r. We're not specifically given lambda, but we know the length and the charge. So this is lambda. Dq from our like trick or like just, yeah, dq equals rho dx. And if we define x, he got from Pythag, he got square root d squared plus x squared as r. So we plug those things in. The limits of integration are from 0 to L from the two ends of the rod. And yeah, if you integrate this, uh Lucas, next slide. Next slide. Yeah, so if you integrate this, you'll get something like this. Uh, yeah, this is like K kind of. Ignore this. Uh, yeah. You can do this on your own if you want to, but we wouldn't do that. Any questions? Yeah. Okay. Next slide. So yeah, practice problem. This is a charged disk. So previously we had like a rod, like an infinite line. Sorry, like a line. Now I'll have a disk with uniform charge density sigma. And so yeah, find the potential at the point P. We'll give you some time to work on that. Oh, by the way, the electric potential is defined to be zero at the center of the, wait, no. Yeah, at the center of the the disk. Wait, no, sorry. I know what I said. Wait, potential should be zero at infinity.
Yeah, and if you guys are stuck, remember that like, potential if potential is zero at infinity, then you know that like if I have a charge like, anywhere on the disk, then the potential due to that charge would just be k times like the amount of that charge divided by the distance to p. So yeah, that'll be the overall idea. So we'll give you a few more minutes and let us know about your progress. Jacob, I think you got the answer. Why don't you explain to everyone how you got it?
Okay. Um, so if you write down this, you got K times dq over R. Okay. Yes, dq is equal to sigma times 2 pi r prime. You are
Yeah.
that. Um, R is also the square root of this squared plus z squared.
Yeah, so
Okay.
see what he's doing. Yeah, sorry. Just to let everyone know, what Jacob's doing right now is he's integrating like these rings of charge, and you know that like in that ring, the distance to P is always the same. And then yeah, so your DQ would be that, and your R is that. So yeah, excellent job done. Yeah, continue, please.
Oh, okay. Okay, so you plug this in. Now, the variable is r prime, and r prime, like the radius, it goes from 0 to the entire radius of the disk, which is r. So you do this, and then you just plug in the numbers. So 2 pi sigma. Oops, not that. Hold on. Eraser that. Hold on. Okay, sure. That's just staying there now. Uh, 2 pi, oh, r prime dr divided by square root of that. Do you want me to like continue the integral or?
Yeah, sure.
Okay. Well, I guess the way that I would evaluate this is I would take like a u substitution. So you would just take u is equal to whatever's inside the square root. So yeah, and we do this because if we were to take the derivative of that, you would see that would equal to 2r prime gr prime, and that would cancel out like the r prime in the numerator. And yes, okay. And you would also have to change the bounds. So you could just plug in the bounds into your expression for u. So that would be r squared plus z squared divided, I mean, on the bottom, it's just z squared because r prime is 0 there. And once you do simplify it, let's see what I got. Okay, so I should have a sigma pi in the numerator, and then that should simplify to 1 over the square root of u du. Yes, and I guess if you were to integrate that using the power rule, you should get k sigma pi. You would also get 2 times the square root of u. Okay, and then you would evaluate that from r squared plus z squared with z squared on the bottom, and then you could just do the difference thing. Let me just write the answer that I got from the top. So you would just get 2 pi uh k sigma, okay, the square root of r squared plus z squared minus the absolute value of z.
Yeah, yeah, I think that's correct. Yeah, excellent job done. Yeah, that was perfect. So, yeah, so just to recap, you're gonna integrate in rings a lot in this disk. So, you can write like your dq using like this, right? And your r would be this, and then after that, it's just a matter of working out this integral right here. And yeah, yeah, great work. Uh, yeah, if anyone has any questions on this, please let us know because it's a like if you're able to do this problem, it's like it's pretty good. Like shows you understand it really well. So yeah.
Yeah, and I know some of you, I don't know if you got the integral wrong or right, but your final answer was a bit off. So, please like review your calculus, like, because it'll be very important for you now. Yeah.
Yep. All right. So I'll clear this and yeah, this is our answer. And yeah, so because like so at the end, I think we got the you might think this is a bit different, but that's actually the same thing because all we did is we turned like at the end we had I believe two we had like on that we had 2 pi times like yeah 2 pi times k, and that's just the same thing as 1 over 2 epsilon 0 because k again that's 1 over 4 pi epsilon 0, so this k is yeah, so we got the same answer. So yeah, great job. Let's move on to the next problem. Yeah. Uh, this is just about batteries. Uh, it's just optional, but how about let's do another question? Uh, I'll just draw it here. So, imagine you have, instead of a finite line, you have an infinite wire, and the wire has charge on it. So say the wire has charge with uh, charge density lambda. And then, so part A, okay, find the electric field as a function of the distance r from the wire. So ER, find ER. And then part B, uh, find the potential as a function of r from the wire and like set potential to be zero at infinity. So yeah, you just have an infinite wire over here. And yeah, the first part is a review of last class, what you guys learned, and the second part, it's more of like, applying like how to find the electric potential from the electric field. So yeah, give that a try. Oh yeah, by the way, just a note for finding VR. I'll how about yeah, don't don't set let's do a general case where potential is zero at a distance r0 from the wire. Okay. So yeah. All right, for time's sake, I'm just gonna start going over it. So okay, let's first find ER, right? So that will just be an application of Gauss's law. So I'm looking at R, right? Distance R away from the wire. So if I make this Gaussian enclosure, right, I'll make a cylinder and it sort of wraps around the wire, right? And then the cylinder, make it like an arbitrary length L, right? And then it has a radius R. Well, then by Gauss's law, right? Then I know that, um, okay, if I want to, first I want to use Gauss's law to find an electric field, right? So I first want to look at what the electric field lines look like, right? So because this is an infinite wire, if you imagine putting like a charge over here, it'll go like directly upwards. It'll always travel radially. You wouldn't expect it to go like deviate left or deviate right because it's an infinite wire and like there's a symmetry involved such that it will only a test charge will only move in the radial direction if I release it. So what does that mean? Well, that means that the electric field lines, like they're always pointing radially outwards. So they're like this is what the electric field lines look like across the wire and also like down and like into and out of the screen, right? So that means that if I'm trying to compute the flux through this Gaussian surface, there's only flux through like there isn't any flux that goes through these two surfaces, right? It's only like this section of the cylinder which has like flux going through it. So we want to find that, right? So we have E, which is because we're looking at this surface over here and it's radially symmetric. So all points on the surface, they're like the same distance away from the perpendicular distance away from the wires. So that means like, my E dot onto the dA, first of all, that would be E times dA, right? Because E would always be that'll always be parallel to the dA. E is constant, so I just pull that out of there. So E times the integral of dA, well, that's just equal to the surface area of the cylinder. Uh, yeah, the surface area of the cylinder, not including these two bases over here, right? So what is that? Well, I know the circumference is 2 pi r, right? And this length is L. So the dA would be uh so 2 pi r L times the E. And that equals the enclosed charge divided by epsilon zero, right? The enclosed charge, that's just lambda times the L, right? Because it has density lambda and it's length L, right? So divided by epsilon zero. So what do we get? So this means that E as a function of R, right? We can write it as equal to, or shoot, right? That equals to lambda divided by 2 pi 2 pi r epsilon zero, which is good because we notice that there's no like we don't have any L term in here, so this is valid no matter what Gaussian surface you choose. And yeah, that's good. So that's part A. Now we want to find part B. But before that, does anybody have any questions on part A? This should just be like an application of Gauss's law. Uh, if you don't remember that, make sure to review the last class recording or the slides. So yeah, I don't see any questions. So let's go to part B. Oh, okay, I'll erase this. Okay, now uh remember what we said V was, right? So shoot, sorry. Okay, so remember, yeah, V equals to uh negative uh the negative integral of our E dot onto the ds, right? Or dr, or whatever you call it, right? Or we can call it dr here. And so we're setting potential to be zero at a distance r0, right? So it would be integral from r0 to r, and this would be v as a function of r, right? So this is just a matter of doing the integral. So we have er over here already, right? So we just plug that in. So it's lambda over 2 pi r epsilon 0. Uh, Notice that E is always parallel to the dr, so that's a good thing, right? So equals to negative integral of that from r0, or I'll let this dummy variable be r prime, right? To not confuse with the r. So then notice that the antiderivative, right? That's uh negative lambda over 2 pi epsilon 0 uh ln of r prime, right? And where r prime goes from r0 uh to r, right? So then you'll see this will be equal to lambda over 2 pi epsilon 0, and then this would be ln of let's see, r0 minus ln of r. And notice this is the same thing as ln of r0 over r. So yeah, our final answer would be, let me write it out a bit more neatly, lambda over 2 pi epsilon 0 uh ln of shoot okay ln of r0 over r. And yeah, and notice that this passes like a sanity check because um like this wire is full of charges. So if I'm if I go from R0 all the way to like, where this is right now. So like if I'm looking at the potential at any point along the wire, you'd expect it to be infinite, right? And that's good because and that's correct, right? And we can confirm that with our formula to make sure our formula is correct because if R is zero, right, then you're getting lambda over 2 pi epsilon 0 times ln of infinity, which is infinite, right? So it shows that this is our correct answer for part B. Yeah. Uh, Part B might have been a bit hard to understand, so let us know if you have any questions. Uh, yeah. For time's sake, I'll just quickly talk about the next slide. Um, you can ask questions about it maybe like after the meeting, maybe send us an email or something. So yeah. Okay, and then this is just about batteries. So we can create a potential difference. So like, you have batteries, right? Uh, on the battery, you'll see like, this is your battery, and then like, oh shoot, I'll draw a battery. So like, you probably have seen batteries before, and then like on the battery, like there's one side that's kind of like this, right? And then on the battery, you see like, for example, 1.5 volts or something. And what does that mean? So basically in the battery, there are chemical reactions that happen. And uh when it, and what it does is that it provides a potential difference. So uh yeah, and that's just due to a chemical process that keeps happening until the battery sort of dies, right? Which is when it can't run this chemical reactions. And basically, if you get a voltmeter and you measure the potential difference between the two sides of the battery, you like hook it up with like this instrument that measures the voltage difference between these two ends of the battery, I'll get it's like 1.5 volts or whatever the voltage is. And yeah, so why this is important is like, later we're gonna learn about circuits, right? So in circuits, like I'm gonna have a wire and maybe I have a resistance and yeah, maybe I connect it with like a light bulb or something, right? And then so I need a potential difference over here because when charges move through, you'll sort of find that it loses potential energy. It loses its potential or like potential energy also, right? Because of these two resistors over here. So every time it runs through this loop, it needs to like, it needs a potential, like, it needs to have a it needs to gain potential so that it can keep running. So like an analogy to this is like, if you're skiing, right? So you're skiing on the slope, like you start over here, which will be, if the current is like let's say the current is running in this direction, right? Then starting on at the top of the slope would be like over here. And as you go through the resistors, you're losing potential, so you're going down the slope. And then once you're at this point over here, then you're at the bottom of the slope. Now, if you want to slide down the slope again, you're gonna need like an elevator or like a ski lift or something to bring you back up. And that's what the potential, well, that's what the battery does. It basically like acts as the ski lift to bring charges back up to a position of higher potential so that the current can keep running. But yeah, we're gonna learn about that in more detail later, but that's an overview of how the batteries work and like their connection to electric potential. So yeah. Don't worry if you didn't understand that because we're just gonna like go over it later. And yeah, so we're actually a bit over time right now, but yeah, so if you guys have any questions about this, feel free to uh like message us on Discord or like send us an email shortly after like maybe today, maybe in a few days, I don't know. We're gonna get you guys the homework problems and like today's slides and also the recording of today's class. And as for the homework, I highly, highly encourage you guys to take a look, attempt at least some of the problems. If you have any progress on it, like even if it's just like an incomplete solution or like you don't have a solution at all, like or you don't even know how to do the problem, like that's okay. Like it's best to just ask someone or ask us for help and like we can help you that way. So that way you guys can improve more. Okay. Yeah. So uh okay, so if you guys have any questions, feel free to ask right now or after class. And yeah. Shamik, do you want to add any notes?
No, yeah. Just at least try the homework and yeah, pretty much it.
Yeah, okay. So I'm gonna stop sharing. And okay, yeah, so that ends today's class. Have a good week, everybody. Yeah, see you.
Thank you.